Hello, I'm Robert Toomey, a research developer working at the Cooperative Institute for Severe and High-Impact Weather Research and Operations. This is an update to the first video in the series covering the continuing progress and work on the W2merger fusion algorithm. After this video, you'll understand more about the issues and changes of the Stage 1 merger as we work towards no caching and becoming VCP agnostic, or in other words, using real-time virtual volumes. You will also learn about things we are doing in order to organize and clean the code and API in a way to make future experiments and changes easier to implement and maintain. So let's begin. We'd like to start by briefly mentioning the stages in our data pipeline. This is just to make it clear where we're at. The stages of W2merger and fusion have been logically divided into three main logical parts. Part of our redesign has been to attempt to separate these stages more clearly in order to allow optimization of each stage. The first stage primarily deals with ingestion of real-time data from every radar we have in the US, Canada, and others. This involves the sine, cosine, refraction, and projection from polar to the final CONUS grid. It also does the heavy work of handling virtual volumes and the values and weights required for stage 2. Any scaling done here is typically vertical scaling. In other words, we make the machine more powerful. The second stage is the collection of all the information processed by each radar into a single 3D cube or 2D cube with multiple height layers. W2merger does this by writing a .raw file to disk, which is then read by a stage 2 for each tile. Tiling a geographical area is how we attempt to horizontally scale the final CONUS product. The third stage is using the final CONUS product to run 3D algorithms, such as a CONUS ecotop algorithm, among others. Typically, these march in the final 3D array to calculate additional 3D products. Our estimate is that stage 1 is actually about 90% complete. We're at the point now where it's mostly bug hunting or comparing old to new. This is probably the hardest part, though, so it's difficult to know when this will be 100%. The stage 2 is either 10% done or 100%, depending on how we do it. If we manage to pass the .raw file successfully to W2merger, that technique might work. However, W2merger requires the cache and VCP information, so it might be better to create a simplified stage 2 for this step. In theory, this stage would be fairly easy. Its job would be to iterate over n radars worth of data and use a weighted method to combine the data. It would then write out a 3D or collection of 2D layers as a lat-long grid or lat-long height grid. The stage 3 currently would still be W2merger. Karen right now runs the algorithms currently as a separate process, so this would work within this framework. Like we said before, we've spent quite a bit of time comparing W2merger to fusion and trying to get them closer in output and dealing with bugs and issues from that. Part of the refactor redesign has been emphasis breaking critical code sections into distinct logical entities. This will allow others at some point to experiment with their own ways of generating the merger data. With this in mind, various plugins have been designed so far, including a terrain blocker, a value blocker, and an elevation volume handler. Each of these plugins offers finer control and resolution of the stage 1 merger process, which handles the calculations for one single radar. We will explain each of these more in detail. The first thing we want to talk about is the learning process involved with terrain blockage and the terrain blockage plugin. Most of the design from the first video has stayed the same. However, the biggest change from W2merger has been shifting to a polar terrain algorithm versus using the CONUS Cartesian grid. This helps with speed using the cacherless method. The big advantage to this is that we only have to calculate terrain blockage per gate center of the radial set, and this is typically faster due to radial sets being much smaller than CONUS resolution. Also, cumulative beam blockage order of magnitude is order of magnitude based on radial when calculated from center to edge along a radial array. The downside is that since radial sets are unique in space-time, we do this for each incoming radial set and cache it. This is a very minor cost in RAM since we add a single 8-bit value per gate for radial sets we are caching anyway, but we could fully normalize a radial set and cache by elevation angle if this ever became an issue. Currently, we still use a DEM file to do simple terrain-based blockages. However, having a plugin here allows the possibility of experimenting with non-DEM methods in the future. Learning about terrain blockage techniques, some mistakes were made. In W2merger's implementation, the beam bottom touching terrain overrides the current cumulative beam blockage to 100%, but only at that location. Also, we found that there were inconsistencies in the values used for Earth's radius between areas of MRMS and our code. This turned out to have a very small effect, but it's still a bug, so worth mentioning. We should be at least consistent in the values used, whatever value we choose for it. Another more interesting mistake was using virtual elevation versus true elevation for generating terrain blockage. This might be obvious to some of you, but we thought it'd be interesting to share. Basically, it turns out that using terrain blockage to generate values between elevations should be dependent on the terrain blockage at the location of the true angles, not the blockage at the interpolated or extrapolated point. Otherwise, you get a false accuracy. The formula on the slide here implies that you want to use the terrain blockage of the upper and lower independently, not the blockage percentage at the center value. This can be debated, but also part of why we have a plugin so different methods can be tried. So just a final thing, we'll show this effect in a picture. The picture on the left uses terrain blockage on upper and lower angles before the values are interpolated. The picture on the right, terrain blockage, is applied post-interpolation using the virtual elevation angle that comes from the CONUS grid. We feel this creates a false smoothness in the output. However, with the terrain plugin ability, you better play with this at some point yourself and maybe create superior methods. So far with terrain blockage, we have two available plugins. The first one is based upon LAC's original terrain blockage. LAC uses a large static virtual radial set that is overlaid over the grid resolution. This method uses a hybrid scan technique described in the paper, the WSR88D rainfall algorithm from 1997. The main issue with it is that in the cashless method is that it has a slow startup time depending on the DEM resolution and CONUS resolution. This appears to be because the method of calculating blockage at a location has limited memory of previous states. In a polar method, we can remember terrain blockage along a radial and use it to calculate cumulative blockage further along the radial. When we changed LACs to use a direct polar method on incoming radial sets, this became fast enough for cashless usability. So before I modify LAC's method to work directly on radial sets, I also experimented with a terrain method based upon the Beck et al. 2003 paper. This was designed as a polar algorithm from the start in order to take advantage of the speed increase. The technique used in it matches techniques used by other libraries out there, such as the wrad-lib Python library and others. Basically, partial beam blockage is calculated using a direct percentage coverage of the full beam width circle caused by terrain. The terrain value used is typically an average of values cutting across the diameter of the beam width. I'm not as concerned now with using this or not, since the slowdown issue was solved with LAC's original, though from my point of view I understand this terrain blockage method much better, and it gave a baseline for comparison to LAC's method. Currently comparing LAC's and mine, we're seeing that LAC's blockage is very slightly hotter, but very comparable. A whole presentation study could probably be done on comparing the two at some point, if anyone's interested. The second plugin that we've created is the value resolver. The idea behind this is to provide a database of information to the plugin that can then be used to calculate the value or values required for that location. Each location corresponds to a cell in the final CONUS output grid. Multiple output values are allowed and probably required. For example, multiple weights plus data values. Everything here then gets passed on to stage 2. W2merger does something similar to this with the different exponential weighted models in stage 2, but here we are talking about a single radar only. This also allows the various methods to be applied for interpolation and application of the terrain, which you would do in your value resolver. So we can show a couple of very simple examples to explain the idea. Here we show a debug value resolver that just takes the virtual azimuth of the grid and uses it for the main output value. So dark here is low value up to blue-white at high value mapping, and we're mapping azimuth from 0 to 359 clockwise. going from the north. So another quick second example here is showing the virtual range from the radar center to use as the final data value. So you can see at the middle it's 0 and outside is what you'd expect. So the third and final plugin so far is the elevation volume plugin. This plugin came later due to feedback and ideas expressed from others. The idea behind this is to allow a plugin with an API for maintaining the virtual volume currently being used. Typically, an elevation volume will be required to maintain a unique sorted list of elevation angles, the time, as well as the data of each radial set. Data is required to not conflict in time and space, so data should age out, and it should also not physically conflict in space with other angles. Priority should also be on newer data over older data. The default simplest elevation volume just maintains the time window and the angles. With the elevation volume plugin, there are 3 methods in the API that need to be fairly responsive for this to work properly. The first is called whenever a new radial set arrives in the system, either from archive or real-time data. Typically, a simple insertion sort seems to work the best here, just to maintain a sorted list of radial sets. The second is a helper method, if required, for allowing time expiration. This is typically only important if you're outputting data multiple times per incoming data set, so it shows up more with heartbeat or synchronized output. The third method that needs to be quick is the lookup from 3D space that gives us the upper and lower elevation angles around a point of interest. This requires searching the list of elevation angles. Currently, for small n, just doing a linear search here is the fastest. This is due to CPU prefetch, L2 caching, and other factors. The plugin model here will also allow others to experiment with more complicated ways of maintaining a virtual volume, including fuzzy logic and or even using BCP information if it's available. So finally, let's get to comparing some images between the 2 methods. We've used W2merger with single radars here to restrict the effect as much as possible. Here is a first image comparison between W2merger and Fusion, focusing on beam bottom touching and projection only. The big gray blob is terrain blockage due to bottom beam touching the ground. We expect to see this fairly close between the 2 methods. Any differences here would expect it to be slight projection differences, floating point round off, and other factors or bugs in the engine itself. Some of the difficulty here is not knowing where or what has bugs, but the assumption has been to treat W2merger as the de facto standard until proven otherwise. So one issue we've been dealing with is the apparent range difference between W2merger and Fusion and trying to narrow down what is causing it. Here we can see a difference grid between W2merger and Fusion where red shows areas of W2merger appearing different from Fusion. Some ideas have been projection differences between angled versus straight interpolation. This effect seemed to be very minor, was eliminated as a possibility. Another idea was that the Earth's radius difference was causing this projection issues, but this was also limited as a cause. The current idea that we have is that it is a difference in allowed values due to the default value resolver using a hard cutoff for beam width. LAC in W2merger is using a cubed weight, which allows for data values to be valid outside the contributing beam width. The good news with this is that it just means the value resolver needs some tweaking and things will match up. Here is another picture with actual data showing merger versus fusion. The value resolver is responsible for all of this output. We're using a very simple linear interpolation here, but we will want to work on this resolver to improve the quality of it. This will probably take input and testing from meteorologists at some point to tweak and improve the logic. So I just want to do a quick acknowledgments page. Lots of people contribute to the ideas and work here, but some of the acknowledgments so far on this project include LAC, of course. Refactoring and redesign is always easier than starting 100% from scratch. Also, Jen, Lynn, Carrie, Chi, all of them gave lots of feedback on terrain and are learning about how things currently work and what we should be striving towards. And then we have Karen, Ken, and Jeff as well for testing feedback and all the time that we've had to experiment with this. And of course, we got Nat at the very bottom. He made the web difference tool that we're using to do the difference comparisons which has really been helpful in tracking down issues and solving some of our previous problems. So now the action list is, so what is the next stage of work will be? The next stage of work will be on the value resolver. Hopefully we'll get rid of the red circle bug, if it is one, or determine exactly what is going on with that. The other plugins can also be tweaked and improved upon. We're wanting to shift soon to getting stage 2 going, where multiple radars are combined into a final product. In theory, this should be easier. This will output at least the 3D, 2D merged products as lat-long grid data, which will allow current W2merger stage 3 to run on them. There are some ideas on how to horizontally scale out stage 2 in a way that will work better than the tiling method we're currently using with W2merger. The main issue with the CONUS tiles with the current method is time synchronization across different systems and the fact that we have to manually configure them, which makes it very difficult from an IT perspective. Also, we're working to continually clean up and improve the API for others. This is very important so that others can have a better chance of understanding and contributing to the merger process. So the algorithm development is based on a newer RAPIO core for MRMS algorithms. This uses a continually modified up-to-date version of the stock algorithm class in MRMS, so any algorithm using that class will be able to transition to RAPIO if wanted. Or the other way around, if you need to develop an algorithm outside the lab that you want to later contribute to NSSL and operations. This uses more modern C++ features, CMake, etc., though it hurts to say C++11 or C++14. Governments move slowly by nature, that's just how it is. So currently the code base is on GitHub at the following address, http://github.com/rapio, though at some point this will probably move to an organization a lot more control from others. So anyway, that's it for now. Have a great day.